Hello everyone. In today's video, we'll be going through GATE 2024 questions and methodology to solve the questions for biomaterials. If you are preparing for the GATE biomedical engineering exam, this video will help you understand how to tackle these questions step by step. Let's begin with the first GATE question from GATE 2024. Bioglass 45S5 as a composition of, this is the question. So we will see what is the answer. Before going to the answer, we will review what is the Bioglass 45S5. Okay, so Bioglass 45S5 is a type of bioactive glass, so that is widely used in biomedical applications, particularly for bone tissue, so engineering and repair. Its composition is known for its ability to bond with bone and promote healing. The standard composition of Bioglass 45S5 is 45 weight percentage of SiO2, that means silicon dioxide, 24.5 weight percentage of Na2O, that's nothing but sodium oxide, and 24.5 weight percentage of CaO, calcium oxide. Lastly, 6.0 weight percentage of P2O5, that's nothing but phosphorus pentoxide. This composition enables the formation of a bioactive layer of hydroxyapatite when the glass comes into contact with body fluids, so which is crucial for bone bonding. Okay, so this is the basic concept of Bioglass 45S5. Now let's review the options. The first option, 45% SiO2 and 5:1 molar ratio of calcium to phosphorus. Okay, I think this is the close to correct composition. Okay, so based on our previous concept, this will be a near about correct answer. Okay, then second option B, 45 weight percentage of hydroxyapatite and 5 weight percentage of SiO2. Okay, then third one, 45 weight percentage of hydroxyapatite and 5:1 molar ratio of CaO and Ca3 TO4 2. Okay, and fourth option, 45 weight percentage of SiO2 and 5 weight percentage of hydroxyapatite. Okay, so I think I will review the answers now. The first question, it contains a 45 weight percentage of SiO2. However, 5:1 molar ratio of calcium to phosphorus, not the exact ratio in Bioglass 45S5. Okay, so which instead involve a mixture of calcium and phosphorus oxides in the composition. So this is the correct answer. Next one, 45 weight percentage of hydroxyapatite and 5 weight percentage of SiO2. This option is incorrect because Bioglass 45S5 does not contain hydroxyapatite as a major component. Okay, so instead it forms hydroxyapatite upon interaction with body fluids. So ultimately, so it will be an incorrect answer. The third option, 45 weight percentage of hydroxyapatite and 5:1 molar ratio of CaO and Ca3 PO4 2. Okay, this is also incorrect because Bioglass 45SV does not contain hydroxyapatite as a direct component, and the ratio of CaO and Ca3PO42 is not applicable in this case. Okay, then fourth option, 45 weight percentage of SiO2 and 5 weight percentage hydroxyapatite. This is also incorrect because Bioglass 45S5 contains 45 weight percentage of SiO2 but does not directly contain the hydroxyapatite in its composition. Okay, from the options we can easily understand all the three options it contains a hydroxyapatite directly. So we can easily identify option A is correct answer. Okay, moving on to the next question. A cylindrical engineered tissue was developed with a diameter of 2 cm, height of 3 cm, and young smallness of 20 megapascal. If an axial tensile force of 10 Newton is applied, the percentage change in the height of tissue is dash percentage. Give your answer round off 2 decimal places. Okay, so this is the question. So let's begin how to solve this question. Okay, to calculate percentage change in the height of the cylindrical engineered tissue under an axial tensile force, we can use Hooke's law for linear deformation, which is expressed as del H equal to F dot L divided by A dot E. Okay, so where F is nothing but axial force, then L is nothing but a original height, then A is nothing but cross-sectional area, then E is Young's modulus. Okay, so I think some of the parameters are given in the problem. Okay, we will see what are the things. Force given in the problem 10 Newton, and length, which means height of the tissue, they have given it's 3 centimeter and Young's modulus is 20 megapascals. Okay, we have to find the area, cross-sectional area A. Okay, now step 1, we calculate the cross-sectional area A. The tissue is cylindrical, so the area A of the cross-section is given by A equal to pi d by 2 whole square. Okay, so this is the formula to find the cross-sectional area of the tissue, since it is cylindrical. Okay, so that D is the diameter of 2 centimeter. For calculating purpose, we are converting into some meter, so it is a 0.02 meter. Okay, so by using this, we can find our area is nothing but 3.1416 into the of -4 square meter. Okay, let's begin step 2. Okay, so calculate the elongation of h, which means nothing but height. Okay, so now substitute the known values into the elongation formula. That's nothing but telling h equal to f dot l divided by a dot e. Okay, so now we found the a value. Okay, already we have these three values. Now we found the a value. By applying these things, we can easily find our height. This change of height is nothing but 0.04774 millimeter. Okay, so this is the answer for us. Okay, but this is not a final answer. Okay, they have asked the percentage. Here we are saying the change of height. Okay, to find the final answer, we have to calculate the step 3. Step 3 is calculating the percentage change in height. Okay, the formula for finding the change of height, del h, percentage del h equal to del h divided by L into 100. Okay, so we know the value of del h and then length. Okay, so by applying this, we can find the answer is 0.1591 percentage. Okay, approximately it converts into rounded off, because they asked in the problem 2 decimal rounded off. So the final answer is the percentage change in the height of the tissue is 0.16 percentage. This is the final answer for this question. Here is the next GATE question from GATE 2024. In an attempt to integrate engineered tissue with native tissue, 3 samples of engineered tissue X, Y, Z with identical material properties were co-cultured adjacent to 3 different native tissues: bone, cartilage, and liver. The adhesive strength of X, Y, Z were observed after 8 weeks as follows. Adhesive strength for X equal to 150 kilopascal, Y equal to 250 kilopascal, Z equal to 350 kilopascal. Match the native tissue that were used to co-culture X, Y, and Z from the following. The first one, liver tissue. Second, articular cartilage. Third one, devitalized bone. Okay. Now we have to match the native tissue with the adhesive strength. Okay, that's the question they have asked. To match the native tissues with the engineered tissue samples based on the adhesive strength data, we need to consider the biological characteristics and adhesive strength typically associated with different native tissues. Okay, so like a liver tissue, it generally has a lower adhesive strength compared to the bone or cartilage because it is less fibrous and has a soft structure. Okay, articular cartilage is a soft and more compliant, and its adhesive strength is typically moderate. Okay, devitalized bone is dense and rigid tissue which would generally exhibit a higher adhesive strength due to its mineralized and structured nature. So now we move to analysis of the answers. Okay, so X with 150 kilopascal adhesive strength is likely to have a co-culture with liver tissue, since liver tissue tends to have a lower adhesive strength. Okay, next one, Y with 250 kilopascal adhesive strength is likely to have a co-cultured with articular cartilage, as a cartilage has moderate adhesive strength. Okay, third one, Z with 350 kilopascal adhesive strength is likely to have a co-cultured with devitalized bone. Okay, so which would exhibit a stronger adhesion due to its rigid mineralized structure. Okay, so the answer is option A. Okay, so other answers are wrong. The option A is the correct answer. Based on the adhesive strength of the native tissues, the answer A is correct one. Okay, thanks for watching this video.